Very good morning, one and all. In the last class, we have started the elements of PCM, and we have given the introduction to each and every element present in the pulse code modulation. Okay, and what is meant by pulse code modulation? This PCM represents the code format or the binary sequence. Okay, so analog signal is converted into binary sequence by using the pulse code modulation, and even we have seen the block diagram. It consists of transmitter section, which in detail consists of low pass filter followed by A to D converter. Okay, and it consists of a channel. Channel possesses number of regenerators, regenerative repeaters. Okay, and the receiving section consists of once again the decoding section followed by low pass filter. And we have seen the importance of input low pass filter. Input low pass filter overcomes the problem of aliasing effect. Okay, that portion we discussed in the earlier classes, and we have started the next block, that is the next element, that is sampling. And what is meant by sampling? It is a process of converting the continuous signal into continuous amplitude sample, mean that it discretizes the time axis with the sampling intervals of Ts having the sampling frequencies of with the sampling rate of Fs, which is greater than or equal to twice that of the sampling rate. Okay, so in order to overcome the problem of aliasing problem, always the sampling frequency should be greater than or equal to Nyquist rate. Okay, and we have initiated the three different types of sampling techniques. Okay, one is the natural sampling. First one is the ideal sampling. In ideal sampling, directly the analog signal is multiplied with the series of impulse train. Okay, so because the impulse train is difficult to generate, what we did in the natural sampling, instead of a series of impulses, series of pulse train is replaced. Okay, series of impulse train is replaced with series of pulse train. That pulse train is multiplied with analog signal to generate a discrete time signal. Okay, so you can call the sample signal also as continuous amplitude sample. Okay, because the amplitude is continuous and time is made discrete. Okay, so that's why you can call the sample signal as continuous amplitude sample. So what is the drawback of natural sampling? In natural sampling, we studied that we are generating the sample signal with the varying amplitudes. Okay, how the amplitudes will differ? The output pulses amplitude is not constant. It varies in accordance with the message signal. Okay, so this kind of varying amplitudes are not compatible with the digital signal. So that's why digital communication. So that's why what we are doing, we are going to make use of flat top sampling. Okay, so whereby this flat top sampling can be this kind of sampling technique will generate pulses of constant amplitudes. Okay, so how can we generate this? Already we have seen the sample and hold circuit. By using the sample and hold circuit, how can we generate pulses of constant amplitude? It makes use of sampling switch and discharge switch, this capacitor is generally called as hold capacitor. And what is the importance of these two switches? Whenever the sampling switch is made close or on, when G1 is on and G2 is off, capacitor charges to the maximum extent of x of t. Here the charging time and discharging time are assumed to be a negligible values. Okay, like less value. Okay, so when G1 is on and G2 is off, capacitor charges to the maximum extent. So the pulse magnitude rises to maximum extent of x of t. Okay, and after the time interval of tau, G2 will make close. Once G2 is close and G1 is made on, what will happen? Capacitor got a path to discharge. So till that time interval, capacitor holds the same value, same magnitude. So that's why the amplitude of the pulses remains constant. Okay, till the time interval of tau. So after the time interval of tau, G2 is on and G1 is off. Once G1 is off, capacitor has no path to charge. So capacitor discharges through G2, which is short at that time. So once again G1 will be made on at each and every sampling intervals. Okay, so that sampling intervals are provided with a sampling frequency, sampling rate of greater than or equal to twice that of 2 FM. So like this, G1 is called as sampling switch because this is made on at sampling intervals. And why G2 is called as discharge switch? Because after every time interval of tau from the sampling interval, G2 is made on. So capacitor will get a path to discharge. So that's why this switch is called as discharge switch. So this capacitor is called as a hold capacitor because the capacitor holds the same value, same magnitude of x of t from the sampling interval of tau for a duration of tau. Okay, so that's why you will get a pulses of flat tops as the output of this sample and hold circuit. That's why this technique is called flat top sampling. Okay, this portion we studied in the last class. So finally, this sample and hold circuit can be able to generate a pulses of constant magnitude. Okay, so this is all about the flat top sampling. This is a working principle. We have seen it in the last class. When G1 is on, when G2 is on, G1 is on at sampling intervals and G2 is on after the time interval of time width of tau. Okay, so now we have also seen the time domain description of flat top sample signal. So how can we generate the flat top sample signal? By using sample and hold circuit. Here in terms of mathematical expression, we can write the sample signal as a convolution of ideal sample signal with the series of pulse train. Okay, so what is this x dash of t? X dash of t is the ideal sample signal, and this you may get a doubt that we are considering ideal sampling here, but practically it is difficult. But we are considering the ideal impulse train, the impulse train, but with pulse width of very minute factor like 0.1 second, like that some pulse width is considered. Okay, so like that the sample signal is generated, and that sample signal, we know that how can you generate ideal sample signal? By taking the product of the message signal with series of impulse train, but these impulses have is like minute width. Okay, next that is taken in convolution with series of pulses. Okay, rectangular pulses. So what is excess of t? Excess of t is a flat top sample signal which you can obtain as a by taking the convolution of the ideal sample signal with the unity amplitude rectangular pulse. Okay, please replace x dash of t. What is x dash of t? The product of x of t and series of impulse train. So how can you represent series of impulse train? Already we represented it as with the impulse function del having impulses located at n intervals. Okay, so where n ranges from minus infinite to plus infinite. Okay, take that in convolution with p of t, you can get the flat top sample signal. So finally, what is a mathematical representation of flat top sample signal? It is just the convolution of the ideal sample signal with the series of pulse train. Okay, you can replace the ideal sample signal with its own expression as x of t into x delta of t, where x delta of t is the impulse train which can be represented with a mathematical function del where the instants are located at NTS. Okay, this is all about the mathematical representation of flat top sample signal. Just the x dash of t in convolution with p of t. That's all. Now here in time domain you have a convolution. So how can you represent that convolution in time domain? The convolution in the time domain can be represented with the multiplication in frequency domain. So in frequency domain, what is the mathematical expression of this flat top sample signal? The product of x dash of t and product of the Fourier transform of x dash of t and the Fourier transform of rectangular pulse. Okay, so this is the Fourier transform. How can you obtain the Fourier transform? Just by taking the product of the Fourier transform of ideal sample signal, that is x dash of omega into p of omega. What is p of omega? P of omega is the Fourier transform of the rectangular pulse train. Okay, so just we represented the product. So what is x dash of omega? X dash of omega is the Fourier transform representation of the ideal sample signal. Already we studied the Fourier transform of ideal sample signal. It consists of the spectrum at sampling intervals, namely n omega s, where omega s is the angular frequency which can be represented as 2 pi fs. Okay, so at every n fs you will have the spectrum. And what is the condition to overcome avoid the overlapping? Always the sampling frequency should be greater than or equal to twice that of the message signal frequency. Then you can overcome the overlapping between each and every spectrum location that exists at NFS, where n ranges from minus infinite to plus infinite. Here in this slide you can observe the spectrum of the flat top sample signal. You can observe the spectrum locations at NFS or n omega s in terms of angular frequency. And what is the condition to avoid the overlapping of all the individual spectrums? To avoid the overlapping, what is the condition? You should consider fs as greater than or equal to 2 fm. Okay, then you can overcome the overlapping. Next, this is the spectrum. So till now we studied the 3 different types of sampling techniques. Those include the ideal sampling, natural sampling and flat top sampling. Why this flat top sampling has lot of advantages over the rest too? Because this flat top sampling generates, it makes use of sample and hold circuit to generate the pulses of flat tops. If we have the pulses with flat tops, it is very much compatible with the digital communication. So that's why flat top sampling is preferred over the other 2 sampling techniques. Okay, so with this we concluded with the sampling section. Now what is the next element in PCM transmitter? Quantization. Okay, so quantization is a process. Okay, so to convert the sample signal into discrete amplitude sample. Okay, let us move to the next slide to discuss the next element, because A to D conversion consists of sampling, quantization and encoding. So we completed the sampling section. Let us move to the next slide to discuss the quantization. Okay, and one more thing, already we concluded with the sampling theorem statement. I think everyone is familiar with this statement. A continuous time signal can be represented in its samples and can be recovered back when the sampling frequency is greater than or equal to twice that of the maximum frequency component of message signal. So this is the sampling theorem statement for low pass signals. Okay, and for band pass signals, for example, the band width be 2 FM. Then what is the sampling theorem statement? A band pass signal of bandwidth 2 FM can be completely recovered from its samples only when its sampling rate Fs is greater than or equal to twice that of the bandwidth. So, but what is the bandwidth of the input signal? 2 FM. So, that's why 2 into 2 FM vastundi. So, you can get 4 FM. Okay. So, I think this one is like you are very much comfortable with these definitions, because you are studying the same definitions from signals and systems. Even in analog communication you studied. Okay, and your assignment for this last week, actually Saturday unexpectedly we didn't get the class, so because holiday, the declared holiday, and because coming to the assignment for the last week, okay, is state and prove the sampling theorem for low pass and band pass signals. Okay, try to complete this assignment by the end of this week. Okay, and by the end of this week I will check and I will see how many of you will complete this assignment. Okay, so take this as assignment for the last week. This is the assignment for the last week session. Okay, now and even I will upload the 3 modules in the today's after completion of this session. I will upload these 3 modules. Okay, next let us see the next element. What is the next element after sampling? So the sampled signal. So what is the sampled signal called as? Continuous amplitude sample. Continuous amplitude sample. That continuous amplitude sample, okay, is converted into discrete amplitude sample. See, always remember that sample is nothing but discrete time signal. Sample is nothing but discrete time signal. So continuous amplitude sample is the output of sampler. Okay, so that is applied to the quantizer. So quantizer converts continuous amplitude sample into discrete amplitude sample. So what it mean here? So this quantizer divides the amplitude axis into certain finite set of levels. Okay, so into how many set of levels you are converting? Into 2 power n number of levels for the n bit encoded sequence. If you want to encode the sequence as n bit sequence, then how many amplitude levels this quantizer will divide? Into 2 power n number of amplitude levels. Okay, now please remember that these amplitude levels are generally called as these discrete amplitude levels. Observe the second point in this slide. Okay, these discrete amplitude levels of the quantizer are generally called as representation levels or reconstruction levels. Okay, and always note one more point, that the quality of the quantizer depends on the number of these representation levels. Okay, these discrete amplitude levels, what are the other, what is the other names? Representation levels or reconstruction levels. Okay, and the quality of the device, which device? Quantizer device. See, here the quantizer is a device and quantization is a process performed by the quantizer. Quantizer is a device that performs quantization. Okay, what this quantizer will do? Divides the amplitude, it makes the amplitude as discrete. How many levels? 2 power n levels for a n bit encoded sequence. What is the other terminology to discrete amplitude levels? Representation levels or reconstruction levels. Okay, now you are dividing the amplitude into certain levels and cheptunam. Okay, now what is the spacing between those two? For example, if you observe the adjacent representation levels, for example, if it is an 3-bit sequence, into how many levels you will divide? This quantizer will divide 2 cube, mean 8 number of levels. For each and every adjacent representation level, we have some spacing. That spacing is generally called as quantum or step size. So what is meant by step size? Step size is a spacing between two adjacent amplitude levels or representation levels. In your textbook, according to your syllabus, we can call it as a step size, but other name is quantum. Okay, so now is this slide okay? We can move, if it is okay, we can move to the next slide. Okay, so what is a quantizer? Quantizer converts the continuous amplitude sample into discrete amplitude sample. It means that it divides the amplitude axis into certain number of representation levels. How many number? 2 power n, where n for a n bit sequence. Okay, so what is the spacing between the two adjacent levels? It is called as step size. It is called as step size. Okay, now let us move to the next slide. So in the next slide, you can see the different types of quantization. Okay, so how many types of quantizations are there? Generally, the process may be either uniform quantization or non-uniform quantization. Now, we told you, already we discussed that the spacing between two adjacent amplitude levels is generally called as step size. Now, if the step size is constant or fixed or uniform throughout the amplitude levels. Ante from 0 to 1 level, from 1 to 2 level, from 2 to 3, 3 to 4 up to 2 power n, if the step size is constant or fixed, then it is called as uniform quantization. Okay, so what is meant by uniform quantization? Here uniform quantization means that its step size is fixed or uniform throughout the representation levels. Okay, now what is the drawback with this uniform step size or fixed step size? If the step size is generally we can move in the fourth module, we can calculate the quantization error. If you while discussion we can see that if the step size is fixed, the quantization error depends on the step size. If the step size is fixed, the quantization error becomes fixed, and if the step size is more, then the step size becomes more, so error will be more. So SNR, it may affect the SNR. Okay, so SNR may become a low value. Okay, like that, if the step size is fixed, it affects the SNR. So that's why this compounding technique is implemented. So what is meant by compounding? It is one of the best example for non-uniform quantization, where the step size is not at all constant. Okay, step size is not uniform. Okay, and it depends on certain non-uniform principle. Mostly it obeys the logarithmic rule. Logarithmic rule. Ante for lower input levels, step size is low. For higher input levels, step size is high. Like that, based on the type of the input magnitude, the step size will depend. Okay, so step size is not uniform or not constant in non-uniform quantization. So what is the best example for non-uniform quantization? Compounding. So it is a combination of compression and expanding So uniform quantization technique is generally of two types. One is mid-rise and mid-tread. Okay, what is the basic difference between this mid-rise and mid-tread? Here the classification is based on the origin location. Based on the origin location, uniform quantization is classified as mid-rise and mid-tread. Okay, based on the location of origin. If the origin lies or locates in the rising position, of step size, okay, rising position of step, it is called as mid-rise. If the origin lies in the tread position of this step size, okay, step variation, it is called as mid-tread uniform quantization. In the case of non-uniform quantization, the response is logarithmic and the example is compounding. Okay, here the step size is not uniform. Out of the two, generally preferred is non-uniform quantization because the uniform quantization may affect the SNR, signal to noise ratio. So that's why non-uniform quantization is preferred. Okay, for providing constant SNR. For providing uniform SNR, this compounding technique is preferred. Okay, now this is about the type classification of quantization. Okay, so what is uniform quantization? Here the step size is uniform or fixed. Okay, and for all the representation levels. Now in the non-uniform quantization, the step size is not at all fixed value for all the representation levels. Okay, because for the low input level, SNR should low, and for the high input level, SNR should be very high. So like that, this non-uniform quantization provides the required amount of SNR to the respective input magnitude level. So the best example for that is compounding. So non-uniform is generally preferred over uniform, and out of this mid-rise and mid-tread, okay, what is mid-rise and mid-tread? Mid-rise and mid-tread is a classification of uniform quantization as well as non-uniform also. It depends on the origin location. Okay, generally mid-tread is preferable. Okay, let us move to the next slide. This is the first type, uniform quantization. So what is uniform quantization? Please observe this slide. If you observe this slide, here we have I represented two different types of uniform quantizations. One is mid-rise, and first figure shows the mid-rise uniform quantization, and second one is mid-tread. Okay, so what is mid-rise quantization? Here the origin, please observe the figure. Here the origin lies in the middle of a rising portion of staircase waveform. Here you can observe the staircase waveform. So what is that staircase waveform? Staircase waveform, like it is the representation of, okay, it is a representation of the discretized amplitude levels in terms of input signal. What is the input to the quantization? What is the input to the quantization? Sample signal. Okay, here x-axis represents the input. Here the input is nothing but the sample signal. Input is nothing but the sample signal. Okay, so that's amplitude levels. Okay, the amplitude of the sample signal is discretized by using several reconstruction levels shown in the y-axis. So what is x-axis? Sample signal. Okay, and what is y-axis? The amplitude axis is discretized into how many number of reconstruction levels? 2 power n number of reconstruction levels. Here let us take, please observe delta. Delta is nothing but the step size. What is delta? Delta is step size. In the mid-rise uniform quantization, in the mid-rise quantization, the y-axis reconstruction levels are generally like in the form of minus 2.5, minus 1.5, minus like 0.5, plus 0.5, like 1.5, 2.5, 3.5, like that, so on. Okay, so it has non-zero level. Okay, now next, please observe the mid-tread. If you observe the mid-tread, so what it consists of? It consists of the representation levels, like odd levels it has. Okay, so like -3, -2, -1, like 0, 1, 2, 3, 4, 5, like that. Mean that it consists of 0 level. Okay, but in the case of mid-rise, it don't consist of 0 level. Please observe the reconstruction levels for mid-rise. If you observe the reconstruction level for mid-rise, if you observe the reconstruction levels for mid-rise, you don't have the 0 level. Okay, it only consists of certain even levels like -2.5, -1.5, like 0.5, -0.5, 0.5, next 1.5, 2.5, 3.5, like that, so on. It don't consist of 0 level. But in the case of mid-tread quantizer, it consists of 0 level. It consists of 0 level. The origin lies in the middle of tread position. So if you observe the origin location, it is in the horizontal position of staircase waveform. But in the case of mid-rise, the origin is in the rising portion of the staircase waveform. Okay, the staircase waveform has some step size. Okay, that step size is represented with delta. So what is delta? Delta is a step size. how many times types this quantization will it's classified? It is classified as mid-rise and mid-tread. In the case of mid-rise, the origin lies in the rising portion. So we don't in the representation levels we don't get the 0 level. Okay, but in the case of mid-tread, because the origin lies in the horizontal position of staircase waveform, you will have the 0 level as one of the reconstruction level or representation level. Okay, that is the basic difference between the mid-rise and mid-tread. Okay, so based on the location of 0 level and non-zero level, this mid-rise and mid-tread is classified. In the mid-rise, please remember one point here. In the mid-rise, because the horizon lies in the rising portion of the staircase waveform, we don't have 0 reconstruction level. Okay, but in the case of mid-tread, we'll have 0 reconstruction level because the origin lies in the horizontal position of staircase waveform. Okay, so this is all about the classification of quantization based on the origin location. Okay, now let us move to the non-uniform quantization. In the non-uniform quantization, the step size is not at all fixed. Okay, here the step size depends on the input magnitude. Okay, so the main drawback of uniform quantization is that it generates uniform SNR for both low input sample as well as for high input magnitude level. Okay, for both low input levels and for high input levels, the SNR is uniform. SNR is uniform. So how can we overcome this problem? You can overcome this problem by considering the non-uniform step size. Non-uniform step size for all the throughout the staircase waveform. Throughout the staircase waveform, if the step size is not uniform or not fixed, then it is called as non-uniform quantization. You can observe the same from the graph. If you observe the x-axis, it consists of input sample, okay, and y-axis is the discrete amplitude and x-axis is discrete time. Okay, so for the input, if the input magnitude is low, then the step size should be low to generate low SNR. Okay, if the input magnitude is high, then you should increase the step size so as to compensate the input magnitude. Okay, because the figure of merit is defined as the ratio of output SNR to input SNR. If the input magnitude is low, then output generated should also be a lower value than the high input signal. Okay, so that's why to generate the low SNR for low input magnitude and high SNR for high input magnitude, this non-uniform quantization considers compounding technique. So compounding technique generally obeys logarithmic response, where it is compressed for low input signals and it is expanded at high input levels. Okay, so this is about the non-uniform quantization, where you will have compression at low input levels and expansion at high input levels. Okay, on the transmitter section, and the reverse portion, okay, reverse principle occurs at the receiver. Okay, so compression in the for the low input signal and expansion for high input signal at the transmitter section, and the reverse principle will take care at the receiving section. So anyhow, we can discuss some more regarding this compounding in the module 5. Okay, so basic principle here is compression for low input signal and expanding for the high input signal. Mean that step size is low for the low input signal and step size is high for the high input signal. You can observe the same from the waveform. Okay, so this is especially to maintain like uniform SNR. How can you provide uniform SNR? Low input signal, low output should be there, and similarly for high input signal, high output should be there, so that you can generate uniform SNR by this non-uniform quantization. Okay, this is by providing the non-uniform step size. That is the basic difference between uniform quantization and non-uniform quantization. Is this clear to everyone? Can we move to the next slide? One of you please respond. Uniform and non-uniform quantization. Please, one of you respond. Is it okay? Please, one of you respond. Is this quantization okay? Can we move to the encoding principle? Say yes or no.
Yes, ma'am.
Okay, ma, thank you. Okay, let us move to the next element. What is the next element? Okay, what is the next element after quantization? So finally, quantizer generates discrete amplitude sample. Okay, what is the output of quantization? Discrete amplitude sample. Now that discrete amplitude sample, okay, is represented in the form of binary sequence, is represented in the form of binary sequence by using this encoder. Okay, what this encoder will do? Encoder converts the discrete amplitude sample into binary sequence. Already I said you that this binary sequence is also called as code sequence, okay, or information sequence or data sequence. So what is quantized signal? Discrete amplitude sample acts as input to the encoder. Okay, it converts into binary sequence which is in the form of zeros and ones. Let us see this graph. Please observe this graph. If you observe this graph, you can see that the quantization levels I represented on the right side. So how many quantization levels are there here? How many quantization levels are there? 0, 1, 2, 3, 4, 5, 6, 7. Mean total 8 number of quantization levels are there. It represents that there are 2 power 2 cube, okay, representation levels. So into how many bits you can encode? Okay, what is the possibility? The possibility is that you can represent it as a 3-bit sequence. Now I represented on the left side of the graph, you can observe the encoded output. Okay, how many, if it is a 3-bit sequence, how many possibilities are there? That range from 000 to 111 to represent as a binary sequence. Okay, now please observe the message signal. If you observe the message signal is sampled at 4 intervals. One is 0 interval t, next 2ts, 3ts. Okay, now what is the magnitude of the message signal at the sample at time period 0? Okay, at whenever t equals to 0 seconds, its magnitude is how much? 100. Its magnitude is actually 4 volts. 4 volts. Now how 4 volts, now you need to represent that 4 volt signal magnitude. That representation level should be encoded into how much into, you need to represent it to a 3-bit sequence. How can you represent that 4 volt signal voltage as a 3-bit sequence? Please observe the same row. If you observe the same row, you will have 100 as the encoded data. That's why down to the graph, down to the modulated signal at t equals to 0 seconds, we represented a 100. Why we represented 100 as the sampled magnitude? Because at sampling interval t equals to 0, its modulating signal voltage is 4 volts. Now that 4 volt representation level, okay, should be converted into a binary sequence. because you are going to represent it as a 3-bit sequence because it has total of 8 levels. Okay, you can represent it as a 3-bit sequence. So 100. So 100 can be replaced by 4-volt magnitude. Now, please observe the graph at time interval t. At time sampling interval t, what is the magnitude? The magnitude is 7 volts. Now that 7-volt magnitude should be encoded. You can encode, the only possibility is 111. So that's why we represented the magnitude as 111. Okay, so the same magnitude is continued till the next sample. Okay, so what is at the next sample? What is the magnitude? 1101. Okay, at the next sample, almost it's in between 5 to 6. Okay, so like that, based on the particular magnitude, the data is encoded. To whichever value it is nearer, the nearer value is generally represented. Okay, at 3t, it has some level in between 1 to 2. Okay, so it is nearer to 1, so he represented 1. Okay, so like that, the data, what you are doing, what is the conclusion here? The quantized amplitude is encoded. How can you encode? If we have 2 cube number of representation levels, you can represent it as a 3-bit sequence. If you have 2 power 4, you can represent it as a 4-bit sequence. Like that, the data is encoded in the form of binary sequence. So what you are doing here? Here you are converting the discrete amplitude sample. In other sense, you can call it as a quantized signal. You are converting the discrete amplitude sample into binary sequence. That binary sequence is a encoded sequence. Okay. Now, this encoded, so now finally you got a binary sequence from the encoder. Next, let us move to the next slide. In the next slide, you can see the, so finally you got the PCM signal. Okay, the encoder generates the PCM signal. Now this PCM signal is applied to the channel. I told you that in the channel we have so many number of regenerative repeaters are there. So in the channel we have so many number of regenerative repeaters are there. Let us see the block diagram of regenerative repeater. Please observe the block diagram here. A repeater, already I told you I used the term equalizer so many times. Okay, and decision making device. It makes use of a threshold level or decision level that is provided by the input magnitude. Okay, please observe the block diagram of repeater. This repeater consists of, okay, the amplifier, okay, next timing circuit, next decision making device. Only 3 elements this repeater consists of. So repeater consists of an amplifier section, timing circuit. Okay, so this timing circuit is especially to generate the synchronized pulse train. So you have used a pulse signal at the transmitter section. Okay, so the same synchronized pulse train should be generated at sampling intervals provided by the sampler data. Okay, so this timing circuit generates a synchronized pulse train at sampling intervals. Here you have these pulses of very short duration located at sampling intervals that you can observe at 4th. Now, next amplifier, and third term is decision making device. So you may like in examination you may get a question regarding these repeaters. How this digital signal can eliminate the noise by using repeaters in the channel. So many repeaters are there in the channel. So each repeater consists of amplifier section, timing circuit, and decision making device. Now, what is the input to the repeater? A distorted PCM signal. Because once the PCM signal is nothing but the encoded sequence. That encoded sequence is fed to the channel. In the channel, the signal may get corrupted with a noise. Okay. Now you can observe at first point, first one is PCM signal, that is the encoder output. That encoder output is once it is applied to the channel media, then the signal will get distorted. At second term, okay, at second position, you can see the distorted PCM. Distorted PCM. Now what this repeater will do? This repeater first amplifies the distorted PCM. Amplifies the distorted PCM. You can observe the amplified distorted PCM as the output of amplifier. Please observe the output of amplifier. The output of amplifier is the amplified, okay, strengthened, distorted PCM. Now this distortion you should be able to eliminate. Okay, okay, amplitude distortion, or so distortion may be of two types. Okay, you may get the signal may get distorted in terms of its amplitude, or it may get like distorted with respect to time. Okay, so its position may differ. So the amplitude distortion may also exist, or sometimes signal may get attenuated, or signal may get distorted with respect to time. Okay, so that's why you need a threshold, you need a decision making device to overcome the attenuation, to overcome the distortion in terms of amplitude, to overcome the distortion in terms of time, phase distortion. Okay, then you need a timing circuit. So the amplified distorted PCM, okay, is applied as input to the decision making device. Based on the PCM component, the timing circuit, it generates, okay, it generates a synchronized pulse train at sampling intervals. Synchronized pulse train at sampling intervals. Okay, now the data is applied to the decision making device. What this decision making device will do? This decision making device compares the PCM signal, or you can say the distorted PCM signal, with the predefined threshold value. Predefined threshold value. This predefined threshold value is provided by the transmitter section. Okay, okay, to generate or to give a decision as 0 or 1. Whenever the distorted PCM magnitude is greater than the threshold, is greater than the decision, then it is taken, then the magnitude is taken as 1. Okay, and the output of the decision making device is 0 if, okay, if the if the PCM signal magnitude is less than the threshold value, then the output is taken as 0. So how can you get the magnitude as 1? The output magnitude is 1 whenever the output magnitude is 1 when the PCM magnitude is greater than threshold. When the distorted PCM magnitude is less than the threshold or the decision level, then the output is 0. Okay, like that, this repeater regenerates the original PCM signal, original PCM from the distorted PCM component. Okay, so so what this repeater consists of? Repeater consists of amplifier section, decision making device, and one of the input to the decision making device is timing circuit. Okay, so what is the input to the repeater? So repeat, in the channel we have so many number of repeaters. Okay, so the distorted PCM, the PCM signal, the encoded signal, okay, once it is fed to the channel, the signal gets distorted. Signal gets distorted. Okay, so the distorted component can be eliminated. The distortion can be eliminated by using these repeaters to generate the data as 0 or 1 based on the decision making device. The decision making device generates the magnitude as 1, generates the magnitude as 1 when the PCM magnitude is greater than threshold. If the PCM magnitude is less than threshold, the decision is taken as 0. Like that, repeaters will regenerate the original PCM from the distorted PCM. Is this repeater clear to everyone? Can we move to the next slide? One of you please respond. Please, one of you respond. Is this repeater circuit clear to everyone? So, please, one of you respond. I0.
Yes, ma'am.
Okay, is this block diagram okay for you? Okay, I call one of you to explain this block diagram. Okay. Aditya, Aditya. Lateral entry, Amma, Aditya.
Madam, madam,
Okay, okay, Amma. Okay, kindly explain the repeater block diagram. Did you understand? Did you understand?
can you repeat it once, madam? I have missed the last points.
Okay, okay, Ma. Okay, I will repeat. No problem. Okay. So this this repeater regenerates the original PCM component from the distorted signal. Okay, let us see how it regenerates. Okay, what is the input to the repeater? So repeater input is a encoded data. Okay, distorted encoded data, because once the encoded data is fed to the channel, the signal may get distorted. Okay, that data, the distorted PCM is collected by the repeater present somewhere in the channel. Okay, now that distorted PCM signal, you can observe at the position 2. At the position 2, you can observe the distorted PCM. The distorted PCM is strengthened by the amplifier section. Strengthened by the amplifier section. Okay, and based on the distorted PCM, this timing circuit generates synchronized pulse train at sampling intervals. At sampling intervals, this timing circuit generates the pulse, like synchronized pulse train. Okay, this is only to generate synchronized sampling intervals. Okay, now the decision making device, it possesses a predefined threshold. So based on the predefined threshold, this decision making device compares the magnitude of the distorted PCM with the threshold at sampling intervals provided by the timing circuit. Okay, so decision making device, what it will do? It will compare the amplitude of distorted PCM obtained from the amplifier with the existing predefined threshold. That predefined threshold is nothing but the decision device. And at what intervals it will compare? At sampling intervals. That sampling intervals are provided by the timing circuit. Okay, so finally decision making device generates the output as 1 when the distorted PCM signal magnitude is greater than threshold. Okay, if the magnitude is less than threshold, if the distorted PCM magnitude is less than threshold, the output is considered as 0. And at what time interval you will consider? That interval provided, sampling intervals provided by the timing circuit. Now is it okay, Aditya?
Yes, madam.
Okay, Ma, thank you. So we can discuss the next slide. Okay, this decoder and low pass filter, this is present in the receiver section. Okay, I think time up. We can continue this in the next class. So what we studied in the today's session, we studied the types of quantization and repeater circuit. Okay, we studied the types of quantization and repeater circuit in the today's session. And almost all transmitter section and channel is over. And the last element is a decoder and low pass filter, which we can continue in the next class. Okay, so wait for 1 second, I will take the attendance. So if you have any doubts, you can ask. Other students can leave the class because like I took the attendance. If those students who have doubts, you can ask the questions, or else you can leave the session. I took the attendance.